So, Lecture 1.1 on performance. Control system performance is measured in the following ways. The first is stability. Control system must be designed such that the plant's output response is stable. Its free response must not diverge from equilibrium is approximately the definition we've been using for stability. And there are some very, very, very minor situations in which you would want a marginally stable system to result. But it's the vast majority of control systems, you want to control the plant so that the output is always going to decay to equilibrium. Now, this is just like bare bones, right? Like if it's not stable, like you're in really bad shape. Like your control system, it can actually, and you might say, oh, well, like most systems seem like they're pretty stable. Well, to a point, a lot of systems are pretty stable. It depends on what your criteria are for like which variables and how it can change. But once you actually put feedback in, you create a situation in which many, many times you can make a stable system go unstable by putting feedback in. So you got to watch out for that. So it's like a little bit dangerous when you put feedback in because you can create an unstable situation. Stability is something that we're going to want to get a sort of metric for eventually, and we're only going to really just touch on it in passing in this course, but it's something called robustness, and we're going to come back to it in a minute. But like the amount of stability that a system has is related to its robustness. So a system could be stable, but like just barely stable, and it could be susceptible to some small change in the parameters or some small unforeseen situation arising, causing it to have catastrophic results. And I don't think this is what, I mean, I don't want to speculate on what really caused the 737 MAX crashes, but I don't think it was a stability thing, but that type of crash where you have something like diverge from what your intended path is, that looks like instability, although I think that it was actually a robustness in a different sense problem. So we'll come back to that at the very end, actually. We'll talk more about robustness in this lecture. So stability is very important, though. Like, you got to have that. That's like bare minimum. It's got to be stable, at least. So we're going to talk about stability, performance for the rest of this week. Yeah?
So by stable, do you mean like through the range of inputs that you predict, you have a normal output?
So there are different ways of defining stability, and we'll talk about them. But the main way we'll use is based on free response. So if you start off with some initial condition that's not at equilibrium, if you disturb it from equilibrium, will it come back to equilibrium or will it just shoot off? So like if you bump it a little bit away, like you can think of it as being like the hill problem, where like you have a hill with a ball on top of it. If you nudge it either direction, it's from equilibrium, it's going to go fall off the hill, right? It's going to fall off the hill. But if you have something like this, it's going to return to the center, which is better. If it's flat, then it's not going to return, but it's not going to fly off either. It's going to be just sort of stay. So this stability concept is like, okay, when you're at equilibrium and you perturb it from equilibrium, is it going to come back? If not, then you're in trouble because it's going to get perturbed from equilibrium at some point. And so what's going to happen to the system at that point? So that's what we mean in the sense of stability in this class mostly. We'll talk about bounded input, bounded output stability, which is a little bit different. It's more focused on the input, the types of inputs, and how they relate to the types of outputs. And bounded input, bounded output stability is another one that is considered in controller design. They're not equivalent, but they're very related concepts. So we'll what's called asymptotic stability, which is the free response based initial condition, let it go, and see if it goes back to equilibrium stability in this class, which is the more common one to consider. Bounded input, bounded output has very specific use cases, including, especially when there's resonance involved, it can be very important to do bounded input, bounded output analysis. So transient response is the second performance criterion we'll consider. So transient response of the plant's output is often important for a control system. The designer may have identified such requirements as the velocity free response must be 0 plus or minus 1 meter per second in 5 seconds and thereafter. Like that might be something that the designer came up with as a requirement based on whatever the system was supposed to do. Another example would be the pressure step response must not overshoot its final value. These sorts of requirements are common. As with many design techniques, some iteration is usually needed in order to meet all of the requirements. So this would be, for transient response, how does it go from its initial condition to some steady state? Does it do that in a way that I like? Does it do it fast enough? Does it stay close enough to the final bound in a certain amount of time? Does it overshoot and oscillate? Maybe that matters to us, maybe it doesn't. So if it's like a human factor situation, like what are the g-forces that the person experiences when this response happens? There might be many considerations in that transient response. Steady state response is the next one. Steady state response of the plant's output is another important consideration of the control system. After the transient response has decayed, the steady state response must meet certain criteria, such as the position steady state response to a unit ramp function must be within 5 millimeters of the desired position. So as we'll find, oftentimes we can't get perfectly zero error in steady state, okay? Well, we can, but we have to change the way our controller works if we're going to do that. So oftentimes what we'll do as our design criteria will be, okay, you just need to be within a certain margin, like a certain tolerance. You could think of it as being a certain tolerance on error in the steady state. And so that brings up a whole slew of considerations as well. So these are the three that we're going to focus on. So stability, transient response, and steady state response. And they're very technical, and they require a good understanding of system dynamics in order to understand how to design for these. But there are others, too, that we're not going to consider very much in this course. So cost is always a consideration in design. Weight might be a consideration. So your control system, if it's going to be on an aircraft, for instance, like the weight of it's going to matter. Complexity. So complexity is important for precisely the reason why it was hard to predict, apparently, that the 737 MAX would force the nose of the plane down and not allow the pilots to regain control of it when a certain sensor went bad. I mean, that seems to be at least a reason that or contributed to those going down. And when you get a very complex system, the number of possible states of the system becomes so large that you can't even, in finite time that you have to design something, you can't even simulate all the possible situations, the possible states of the system. And it's very hard to guarantee you won't get into some bad state. So that's probably the main reason why we prefer simpler controller designs and simpler system design in general, because it's really hard to predict what's going to happen in complex systems. And even if you feel really confident that you've done a great job, there are some situations that sometimes elude us, and they can cause problems. And especially if it's like a critical situation where there's like human life involved, then you really need to be cautious about the complexity of your system. So that's another factor. One of the most important of these is robustness, the control system's ability to perform as desired when system parameters change from their nominal values. This is important because the parameters of any implementation of a control system will differ from their nominal values at least slightly. So this is where we're going to get into, like, okay, it's stable, but how stable is it? Like, if it's stable, but if you change the actual, say, torque constant of the motor by 10% because somebody switched out the motor and it had a different torque constant by just, like, not a ton, but a little bit, what happens to your controller design? Does it go unstable at that point? And if so, that's a very dangerous place to live. Like, you don't want to live there. You want to live where you could change parameters pretty significantly, or at least, to a reasonable extent, without having the controller go unstable or perform really poorly. Okay, so robustness is a really important concept. We're going to talk about it like throughout this text, but you can actually focus on robustness as a topic of study directly. We'll just pepper it in. All right, so that's all I've got for today, and I'll see you guys on Wednesday.